Okay, today's lesson, 2.7, is about dilations. A dilation is a transformation in which a figure is made larger or smaller with respect to a point called the center of dilation. We are going to tell whether the blue figure is a dilation of the red figure. So basically we want to look to see if it has changed size. So after a dilation, the figure is similar to the original. So in A, we can see that the lines connecting the corresponding vertices will meet at a point. So the blue figure is a dilation. We can see that point of dilation. In B, the figures have the same size and shape. So they're still congruent, but the red figure slides to form the blue figure, so it's more of a translation, not a dilation. So no, B is not a dilation. So on your own, you can tell whether the blue figure is a dilation of the red figure and explain. So in the first one, we look at them and they do appear to be congruent, which does not make it a dilation. Remember, a dilation, by definition, will make it smaller or larger. So since it has not changed size, it is congruent. We look to see what else it is. So tell whether it is a dilation. No. This is a reflection. Okay. For the next one, we can see that it has changed size. So they're similar, okay? And then you kind of want to maybe line it up. You can use an index card or a ruler. I'll try to do my best. Obviously in a textbook you're not going to be able to do it unless you redraw the figures perfectly. And I know I'm going to have a terrible time here, but I'll give it my best shot. Well, that's not going to work. I need to make it very thin. And that still might not work. Okay. So I'll do my best without a ruler because I can't get a ruler in close enough here. So I'll just connect these 2 points. Hold on. Okay. I'll connect these 2 points. Oh, sorry about that. But if you used a straight edge, you could see that there would be somewhere out in here, they would all intersect from a center of dilation. Okay, so that would be your center point. So the answer for this is yes. This was no. Okay. In a dilation, the original figure and its image are similar. The ratio of the side lengths of the image to the corresponding side length of the original is the scale factor. So the ratio of image to original is how you would figure out what the scale factor is. So here's a picture, and you can see A, B, and C has been dilated or enlarged is one way to describe that. So the way we describe our dilations is that if the scale factor is greater than 1, it's an enlargement. It will get bigger. But if it's a decimal or a fraction between 0 and 1, it's a reduction and it'll get smaller. Okay? And here's the algebra notation where we are multiplying the x-coordinate and the y-coordinate both by the same scale factor. All right. So let's take a look at example 2 for dilating the figure. So you can see that the original A, B, and C has been drawn, and then after a scale factor of 3, and we have listed the coordinates for the prime notation. So if you multiply each x and each y, right here is the work that you could show to actually get the solution, okay? And we would say that it's an enlargement. All right? Now let's try this again, but this time we are going to dilate by a scale factor of 2. Okay. So dilating by a scale factor of 2. So to show your work, you could show that you're going to take 2 times the x-coordinate and 2 times the y-coordinate. So 2 times 1 and 2 times 3 for A, 2 times 2 and 2 times 3 for B, and 2 times 2, and 2 times 1 for C. I'm going to give these a notation, and I'm going to change the color here maybe to green, and I'll call them C double prime. So for C double prime I would have, because I left the blue figure on the graph, I'll give it the double notation, but one notation is fine. 2, 6, oh sorry, that was A. B double prime would be 4, 6, and C double prime would be 4, 2. So that if I graph them at 2 and 6, at 4 and 6, and at 4 and 2, I could then connect them and draw my triangle. And you can also see how they intersect with those lines that are showing the center of dilation. Okay, but this would be listing the coordinates after a dilation with a scale factor of 2. All right, so the other thing that it asked you to do, which we didn't really do, but it said to identify the dilation. So the last one would have been an enlargement, okay? So that example 3 is a reduction. So in example 3, you can see that when you have a fraction or a decimal, 0.5 is the same as 1/2, you still multiply everything by that scale factor to get your new vertices and graph it. And then you can also name the dilation. This is a reduction. So let's do a reduction. So in this one, we want to multiply everything by 1/4. So 1/4 of -4 and 1/4 of -6. And then 1/4 of 8, 1/4 of 4, and 1/4 of 8, and 1/4 of 4, and 1/4 of -6. And I'll give it the double notation again. So 1/4 times a -4, it's like dividing by 4, is a -1. -6 divided by 4 is -1.5. Eight divided by 4 is 2. And so if I graph it on this graph, pay attention to the scale of your x and y graphs and axes, because these are counting by 2's. So to do -1, -1.5, it would be somewhere around there. And then -1, 2 would be up here, 1, 2, and 1, -1/2. And a very thick line to give you my reduction by a scale factor of 1/4. All right, so now we're going to explore using more than one transformation, and one of them would include a dilation. So here's the vertices of a trapezoid, A, B, and C. The first thing is to dilate it by a scale factor of 2, and you get A prime, B prime, C prime, and D prime, and then translate it so that your answer to this question is to find the coordinates of the image. All right, so there is the image, and here are those coordinates. So we are going to do this. Remember that when you're doing a translation, reflection, and rotation, it is congruent to whatever you are translating, reflecting, and rotating. The image of a dilation is similar. Okay. So, here we go. We have our original vertices of A, B, and C. And I'll do that in red. So we have A at -2, -1. This is from that example. B, -1, 1. C, 0, 1. And D, 0, -1. And I've already graphed that trapezoid. Okay, so now we're going to do a scale factor of 3. So I'll do this in B. So I will have 3 times x and 3 times y, because my scale factor is 3. Because that number 3, the factor, is greater than 1, it will be an enlargement. So A prime would be 3 times -2, which is -6, and 3 times -1, which is -3. B prime, 3 times -1, and 3 times 1. C prime, 3 times 0, and 3 times 1. D prime, 3 times 0, and 3 times -1. So I would graph this image. Okay, so -6, -3, -3, 3, 0, 3, and 0, -3. And I would draw it. Terrible, terrible straight lines here. Okay, that's A prime, B prime, C prime, and D prime. Now I'm going to do 180 about vertex C. So when you do a 180 rotation about a vertex, okay, first of all, we know that that vertex remains the same. The easiest one to draw is we need a 180-degree angle formed between C and B, so that's B prime is 3 units away, so then B double prime has to be 3 units away. Okay. The next one that would be easy would be D double prime, because it would have to be 180 degrees from the C, because it's rotating about vertice C, and so I'm going to run out of space here on the top, so I'm going to make this go 6, 7, 8, and 9. All right, so it would be up here, okay, for D double prime, and that would connect. Okay, so then I look at A, and again, A has to go 180 degrees. All right, so B is 1, 2, 3, 4, 5, 6 units on the y-axis, and 3, 1, 2, 3. So I would count up from B, 1, 2, 3, 4, 5, 6, it'll be at 9, and then 1, 2, 3, and I kind of got off my beaten path there a little bit, again without a straight edge. So there is A double prime. So then I can connect them. So A double prime, and if I look at where that is, 6, 9. B double prime is 3, 3. C double prime stayed where it was at 0, 3, and D double prime is at 0, 9 after the series of these transformations. Okay? And then finally, our last example is to describe a sequence of transformations. So if you recall, our prior definition is that the scale factor is the ratio of the image to the original, all right? And so if we look at the original, we have this side length right here, the corresponding side length, or we could even look at the vertices. So in the red, the first point that we see, you know, right here, is at 4, -2. And that corresponding vertice is right there, at 2, comma, negative 1. So if we look at to find how much it was reduced from the red to the dashed line blue, the pre-image right there in between, we could take the x-coordinate and say 2 over 4 would be equal to our k value. And if we simplified that, that's how we could get a scale factor of 1/2. Okay, and that's what it says, that the original was first dilated, okay, with respect to the origin of a scale factor of 1/2, and then that dilation was reflected over the x-axis to get to the final blue image. So there's a series of 2 things that we could do. It is possible that we could have done these in reversed order. We could have reflected first over x and then done a scale factor. Okay, so you might have to draw the reflection first and then compare the same things, because you would be able to calculate the same scale factor. Remember, the scale factor is defined as the ratio of the image to the original.